Good evening, everybody. So today we'll just still continue with the different other coordination numbers of metal complexes. So we have started our journey from a very low coordination number. We have also seen some examples for the coordination number of 1. So this is not very usual, but is a really unusual situation where we can consider a situation where we can have a coordination number 1. So just simply if we go on increasing the number of ligands around the metal ion center or some other non-metal center. So it can be our metal center where we see that this metal center having some charge on it, it can be bivalent or trivalent. Then we can put several ligands around it. So we get a corresponding situation if we are just considering, today we are starting from there basically, a coordination number of 5. So ML5 would be the immediate situation where we can accommodate 5 ligands around the central metal ion. In the same way, if we just consider that a non-metal center is there, it can be phosphorus, it can be bromine, or it can be some other non-metal center. And in that case also, if we just see that if the ligands are now the fluorine atom, so in that case also very much similar to that of the metal complex, where we can see that a particular center is again surrounding in a corresponding typical geometry where we can have the phosphorus fluorine bond or the Br F bond, or in some other cases some other bigger type of geometry we can have. So side by side we are just comparing some examples only, that how we can accommodate a situation where we have the metal ligand assembly and in some other case a typical fluoride, chloride, bromide or any other metal fluoride or metal chloride is there. Because we can go up to a situation where we can have the other transition metal ions, say iron from the first series or ruthenium from the 4D series or osmium from the 5D. We see in all these cases there are the chances of having the corresponding fluoride salt or corresponding chloride salt or corresponding bromide salt. So way the metal salts, the corresponding halides are there, in the same fashion these metal ions or some other metal ions, say tantalum etc., can form the corresponding metal salt or as the corresponding fluoride when they are binding to the fluoride center. In that particular case, what we are just thinking that as we go for higher coordination number beyond 4, we are just increasing the size of the corresponding central element and the size of the ligand is also less. So we can have a bigger size and we can have the smaller atoms surrounding the species. So at one case we see that we can have the corresponding number of the smaller spheres which are our ligand in a typical situation where we can have, this is one square plane above this bigger sphere and this is another square plane below the corresponding bigger sphere. So we have to consider all these, that means we have to consider in that particular situation as a corresponding coordination number as if they are all binding to the central element. So we can have a corresponding coordination number of 1, 2, 3, 4, 5, 6, 7, 8. So in this way we can just go up from one level to the other and finding how they are involving in the corresponding coordination numbers of different elements. So in this third part of this class, we are just considering the different types of coordination numbers, and one example we have started discussing, that is the vanadilyl acetyl acetonate, which is VOACAC whole 2. And all we know that the acetyl acetone molecule is providing 2 oxygen atoms to the metal center through deprotonation. So it is a mononegative ligand. So one half is binding like this. In the same way, the other half is also binding to the metal center, and we have a vanadium oxygen bond as the vanadyl species. So this particular situation is very different compared to the other, because we can have that all these vanadium oxygen bonds what we are having, they are of vanadium oxygen single bond, and one is vanadium oxygen double bond. So definitely this bond length will be shorter compared to that of our vanadium oxygen single bond. And all these 4 oxygen atoms which are coming from the 2 acetyl acetonate ligands will remain in a square planar geometry. So this is our corresponding square planar geometry, and when all 4 positions in a particular square plane are occupied, we don't have any other option to think of that the vanadium double bond oxygen will be either above the plane, either above this particular square plane or below this particular square plane. So what we get, we are basically getting a square pyramidal geometry. Is a square plane and the pyramid is the corresponding vanadium oxygen double bond. And we have some room for these reactions. That means we have some positions, that means if some groups like pyridine is allowed to react with this particular vanadilyl acetyl acetonate molecule, it can go and start finding some position to have a corresponding vanadium nitrogen bond, which would be definitely longer, corresponding to this vanadium oxygen and the vanadium double bond oxygen. But in that particular situation, we have the option that the situation will go from a typical square pyramidal geometry to an distorted octahedral geometry. So not only from the structural point of view, but also some other reactivity pattern, we can see how these particular new groups are coming and entering to the vanadium center or vanadium coordination sphere, and how this particular double bond will react further, because whenever we can think of a oxygen double bond, an oxygen double bond to any metal center, at the same time we can consider that through one step of deprotonation it can go to HO minus. Again, another step of deprotonation will lead to O2 minus, which is the oxo anion, and this particular one is our typical oxo anion. So when it is in the isolated form, that means when it is simply present as O2 minus, we can consider it as a corresponding oxidoligand, and definitely its corresponding property towards the protons which has been lost from hydroxide group or the hydroxide group which was generated from the water molecule, the affinity for their getting back the corresponding proton to all these anionic species would be different when it is bound to a particular metal center such as vanadium in +4 oxidation state. This particular vanadium center is in +4 oxidation state. So what we will see that whenever we have the corresponding one, this is the most stable species which can be synthesized, what we have seen in my previous class, that how we can synthesize it from V2O5 vanadium pentoxide. It can be generated from vanadium pentoxide. So once it is formed, it is the most stable form is the corresponding vanadium oxo compound or the vanadyl acetyl acetonate compound. But there will be chance that it can convert this vanadium double bond O can be converted like the conversion of oxido group to the hydroxido group or to the water molecule. So we can have the corresponding situation where we can put one proton or another proton to this oxido oxygen on the vanadium center. So that will give us some information that how we can think of some reactivity pattern on this vanadium acetyl acetone molecule, because it is well known that it is a very good reagent in the epoxidation of allylic alcohol. It's a special type of alcohol where the allylic group is present in combination with tertiary butyl hydroperoxide. So tertiary butyl hydroperoxide which is used this is a typical organic peroxide, and that organic peroxide can also give rise to the corresponding hydroperoxide anion, and it can deliver to the system the corresponding oxido anion for the reaction which is known as the corresponding epoxidation reaction. So if we have a corresponding allylic group for the can consider as it's their double bond, so the corresponding epoxidation can take place on it, and we get the corresponding epoxide, and this is very much catalyzed by VO ACAC whole 2. So we have a typical coordination number for this which is very much useful for its corresponding reaction. So not only the metal ion, its coordination number, its coordination geometry, but also the corresponding reagent as well as the nature of these ligands are useful for a particular coordination compound to function as a good catalyst, because this is the most important aspect of this particular part of chemistry of these elements, that they can also nicely perform the job of a good catalyst. But the corresponding individual metal salt, say it is V2O5 or any other vanadyl compound, which may not be useful for this simple epoxidation reaction of allylic alcohols. So we can take only the help of one particular type of the ligand system, that means the ACAC ligand system, which is bound to the vanadyl system and deliver the corresponding catalytic activity. Similarly, just now what we are discussing, that if we have instead of this vanadium center, if we can have the corresponding bromine as the central part, and we have the corresponding interhalogen type of compound, that BrF5, So this will also have a similar geometry corresponding to BrF5. Here vanadium center is occupying the bromine position. This oxygen is occupying the axial oxygen, which is double bonded to the vanadium center, and 4 other oxygen atoms of the ACAC ligand is occupying the 4 other positions in the equatorial position of the square plane, giving rise to VO4 plane in this particular case. So what we see in case of the BrF5 molecule also, which has a similar geometry to that of our this complex of vanadium, is also square pyramidal in geometry. And when this fluorine, which is they are present as the corresponding axial ligand, we have a bond angle of close to 90 degree, but it's a little bit deviated, which is 84.8 degree. So that this means that this fluorine is little bit tilted toward this particular fluorine, making the angle less than 90 degree. And the bond angles are also, these bond angles are different. They are 1.77 angstrom, but this particular one is 1.68 angstrom, which is axial in nature. So not only this complex, but also we get some inorganic compound which has a close similarity of their structure, which is square pyramidal in geometry. So this particular ball and stick model will also depict the geometry of either the vanadilyl acetyl acetone molecule or the BrF5 molecule, showing nicely the corresponding square plane where we have this particular square plane is there, and the apical side is occupied by this either the fluorine atom in case of BrF5 or oxygen of this vanadilyl acetyl acetone molecule. So we have now in our hand the corresponding square pyramidal geometry for a typical coordination number of 5. So if we can have any other alternative geometry which is 5 coordinates, so all these 5 coordinate complexes can have some differences in energies. So we can state in this fashion the energies of various geometries. If there are 2 possibilities of these 2 geometries, already we have discussed that out of these 2 geometries, one is just now we have concluded our discussion about the corresponding square pyramidal geometry, and the second one is the trigonal bipyramidal geometry. So if they differ little from one geometry to the other, we see that these complexes can function as a corresponding frictional molecule. So a frictional molecule is the has that with slight energy change from one form to the other, they basically go from one structure to the other. So any spectroscopic technique or any other physical technique, if we use to monitor the corresponding structure, it is very difficult to monitor the corresponding geometry in one form only, because they are continuously interchanging from one form to the other. So one such example is a very simple example is iron pentacarbonyl compound. So this iron pentacarbonyl compound will be very much similar to that of what we are seeing for vanadilyl acetyl acetone molecule or BrF5 molecule. So this pentacarbonyl compound has one form which is trigonal bipyramidal in geometry. So this TBP geometry is present, and when we have this corresponding polyhedron, so the corresponding polyhedron is trigonal bipyramidal in structure. So in one particular form, this will be stabilized with this geometry. And if we have these two geometries which are interconvertible, means we can go from one particular geometry to the other with a slight energy change. So if we just move from a trigonal bipyramidal geometry to a square pyramidal or vice versa, we see that one isomer will have a different geometry to that of the other, and we consider a typical pseudo rotation. And Berry proposed this particular pseudo rotation in this particular molecule. That's why it's known as Berry's pseudo rotation, in which a particular geometry in TBP is moving towards square pyramidal isomer and then again becomes trigonal bipyramidal. But the initially equatorial carbonyl is now axial. So if this particular molecule can be monitored for their geometry by simple, say, C13 NMR, the carbon 13 NMR will be a very good tool to identify these two geometries. And we find that the corresponding position for the axial and equatorial, that means which are above the trigonal plane and which are in plane, they resonate at different frequencies for their corresponding C13 signal in NMR. Then once they move from one geometry to the other, it's very difficult to identify these two groups of carbon monoxide ligands differently, because one, when it is present in the equatorial geometry, it becomes axial, and axial molecules of carbon monoxide will become equatorial again. So they are interconvertible from one form to the other. So this is the typical geometry which we can show, is that this is the trigonal plane, and one above this trigonal plane and another below the trigonal plane. So considering these three spheres, these are the corresponding carbon monoxide groups. So these three spheres, basically they are forming this particular trigonal plane. So this trigonal plane, one above is this sphere and another below is this sphere, and we get a corresponding trigonal bipyramidal geometry. So how this particular pseudo rotation can take place is very easy to understand from there, that all these three, that means these three, so this also we can consider they are in one particular plane, will remain intact. Only these two carbon monoxide molecules, the arrow, the labeled as two arrows, they will move in these two directions on the left hand side of figure A. And when they are moving in this particular direction and they are forming, this is the carbon atom and this is also the carbon atom for the carbon monoxide molecule, and this red sphere is the iron. So initially when they are present in this trigonal bipyramidal geometry, this carbon iron carbon bond is 120 degree, and due to the movement we are just increasing the corresponding bond angle between carbon iron carbon from 120 degree to 180 degree. It has become 180 degree in this particular situation. And at this point the geometry is changing, that means all these four carbon monoxide molecules have come to a particular square plane. This is the square plane. First one, second one, third one and fourth one. They are present in this square plane. And this particular carbon monoxide has become the corresponding pyramidal one. So from this direction we get a square pyramidal geometry. So TBP geometry has changed to a square pyramidal geometry. So is the fractional molecule in one particular form is changing to the other form, and from this particular form we can get a different type of square pyramidal to trigonal bipyramidal geometry if we go for, because initially in figure A these two carbon monoxide molecules are moving, from here to left and from here to left again. Now these two carbon monoxide molecules which have already moved, they will remain stationary. Only the other two in the shown arrow position, so these two carbon monoxide molecules move in this direction, such that we have this carbon iron carbon bond originally at 180 degree will now decrease and will make the corresponding, including this one, to the corresponding trigonal plane. So after movement we have now the new trigonal plane like this, and carbon iron carbon bond which was 180 degree in figure B will be 120 degree in figure C, and as a result we get a new trigonal plane which is completely different from figure A. Here the trigonal plane is forming through these three spheres. Now we have three other spheres which are already present over here, as the axial carbon monoxide is now equatorial and equatorial carbon monoxide will be now axial. So these two types of interchanges is very difficult to identify which carbon monoxide molecule will be axial and which one is equatorial in any spectroscopic measurement such as C13 NMR spectroscopy. So we get a changed trigonal bipyramidal geometry, but the geometrical pattern will be close to that of a new trigonal bipyramidal one. So which is true for a molecule which we consider as a homoleptic molecule. That means M is present which has bound to 5 ligand system and all the ligand systems are same. That means the nature of the ligands are all same, and we call them as they are homoleptic ligands binding same type of ligand to the metal center. So when they are changing from trigonal bipyramidal to a square pyramidal geometry to again TBP geometry, we are not getting back the original geometry in this particular case, and the corresponding axial groups or axial molecules which are present from these groups are changing to equatorial position and equatorial groups are changing towards the axial position. So therefore in the spectroscopic signature or in the spectrum we get the corresponding signal positions which will be averaged out. That means if we have one position for the corresponding axial one and another position for the equatorial one, so carbon monoxide, the carbon signal which is coming for axial and which is coming for equatorial, and if we can go for corresponding temperature dependence, that means if we just simply increase the temperature, that means we have very fast interconversion between these two geometries, TBP to square P and the square P to TBP, and which are becoming very fast, and we will just end up with some average signal which will merge these two signals into one. So that is the basic idea, that how we can just differentiate these two types of groups. If we just low down, we can go down to a lower temperature. That means we can freeze these two individual structures. That means if we can freeze this TBP structure and this square pyramidal structure, then these two having two types of say COs groups attached to the iron center for TBP geometry and two types for the square pyramidal geometry, and if their positions for identifications are all different, theoretically we should have 4 signals, 2 from this square pyramidal geometry and 2 from this trigonal bipyramidal geometry, and much more complex pattern we can have for this type of pseudo rotation for 2 different types of geometries. So if we next move to the corresponding higher one, that means the coordination number of 6. And in that situation, we have the most important geometry we can have there is the corresponding octahedral geometry. So 6 groups of ligands which are bound to the metal center, 4 will be in this particular plane, 1 will be above this plane and another will be below this plane, and the typical polyhedral structure has 8 faces, 4 above and 4 below the square plane, so that is known as therefore the octahedron, and the corresponding geometry is the octahedral geometry, and the metal complex is definitely the corresponding octahedral metal complex. So we'll be now talking about the corresponding coordination number of 6. So most important example which are plenty in number, and we have large number of all these examples where the coordination number of 6 is only found in these octahedral structures. One such example is trans tetramine dichlorotetramine cobalt 3 compound, and this example we have earlier also seen, which is a metal A4B2 type of compound. So when we fix this particular geometry and we get a corresponding octahedral geometry, and we can have these 2 positions. So B2 can have 2 positions, and these 2 positions, that means BMB angle, we can have 2 types of angles. One will be close to 90 degree and another will be close to 180 degree. So when this BMB angle, which is also true for square planar geometry, we get when these are opposite to each other, we get a corresponding isomer as trans isomer. We'll all discuss this when we study the isomerism, and this is the corresponding geometry which is a cis geometry. So when we talk about the corresponding positions of B and B in a octahedral geometry, so immediately considering this particular square plane, we can consider that we have 90 degree situation in this particular case, so it would be cis geometry. Similarly, we should also have some idea how we get the corresponding geometry if the position of B's are like this. So this is considering this position, and this position is also another square plane. So in this particular case also we have the BMB angle which is close to 90 degree. So this would also be a cis geometry. So we can similarly change the positions not only in this particular square plane but in other square plane, because in this side also we have another square plane. So we can have other positions at the same time. So when 4 ammonia molecules are attached to the cobalt center and 2 Cl as the ligand, we get the trans when the chlorine cobalt chlorine bond angle is 180 degree. When chlorine cobalt chlorine angle is 90 degree, close to 90 degree, we get the corresponding isomer as the cis isomer. We label it as cis CONH3 whole 4 Cl2 plus. So this is the corresponding structure. These green spheres are the corresponding chlorine atom, and 4 NH3 molecules are in plane. So this in plane is little bit crowded, is surrounded by 4 NH3 groups which are blue in color. So you have 4 cobalt nitrogen bonds in this particular square plane, and the green cobalt chlorine bond and this green sphere bound to the cobalt center, one is above the square plane and another is below the square plane. Similarly, this is the situation where we see that if we consider this particular square plane, already we have this particular chlorine atom in it. So these two positions are therefore important. If we interchange these two positions, bring the chlorine to the nitrogen position and the nitrogen to the chlorine position. So these two positions, if these two positions are interchanged, we get the corresponding cis compound. So cis compound will be in our hand and we get another geometry in the octahedral coordinations. Similarly, if we have 3 bidentate ligands, so these are COO. COO is the oxalate anion. So oxalate is a very good bidentate ligand system binding to the metal center with 2 oxygen atoms. And when these 2 oxygen atoms are bound to the iron center, we get 1 bidentate chelation over here, second from here and third from here. So it's basically iron trischelate, and since the oxalate anion has 2 negative charge, we get overall 3 into 2 6 minus negative charge, and iron is in +3 oxidation state. So after balancing the negative charge of 6 units by 3 positive units from the metal center, will remain with 3 negative charges, which should be counterbalanced by the corresponding potassium ion given to the center. Therefore, we get a corresponding potassium salt of the corresponding tris oxalato compound. So is known as potassium tris oxalatoferrate 3. And since this molecule don't have any other second type of donor atom, we don't get the corresponding trans geometry or the cis geometry out of this molecule, and only again a homoleptic situation is occurring there, and FeO6 coordination sphere is generated through tris binding of the 3 oxalato groups to the ferric iron. So this is the situation in one more case where we have the corresponding acetyl acetone group. Just now we have seen in case of vanadium also, and this delta nomenclature will shortly discuss it about what is the meaning of this delta nomenclature. Before any tris chelation, this is the tris chelate similar to that of our oxalate chelation, is ACAC chelation, and manganese is in +3 oxidation state, and ACAC ligand is mononegative ligand. So this mononegative ACAC ligand will give rise to 3 chelation, and these red spheres are the oxygen atoms from the ACAC ligand. This is from the first ligand, this is from the second ligand, and this is from the third ligand. And the interesting property for the manganese in the trivalent state, which is a 3D4 system, is that unequal occupancy of the 2 levels, that means the T2G and EG level, that we'll discuss when we'll discuss about the electronic structures of these molecules and the crystal field theory. We'll find that there will be some Jahn-Teller elongation, but right now what we can consider it is that we have a tetragonal plane, this particular type of plane where we have a square plane. So we have a tetragonal plane, and above this tetragonal plane we have 1 oxygen, and below this tetragonal plane we have another oxygen. And if this particular axis, if we consider this as the z axis, when this is the x axis, 1 oxygen manganese oxygen axis is the x axis, second oxygen manganese oxygen is the y axis, so the third is the z axis. So we will find this particular elongation, that this bond, that means along Z axis the manganese oxygen bonds are longer compared to the manganese oxygen bonds which are available in the x axis and the y axis. So the electronic situation is such that we have an elongated octahedral geometry. Similarly, if we just simply go for ethylene diamine, this particular ligand is our ethylene diamine, and when two nitrogen atoms of the ethylene diamine molecule, what we know that so this particular ligand is also similar what we are seeing just now to oxalate anion or ACAC, acetyl acetone anion. So from these three examples we basically three different types of ligands, where we have, in case of oxalate ligand we have after deprotonation 2 negative charge. In case of acetyl acetone we have 1 negative charge, and in case of ethylene diamine we don't have any other charge, which is a neutral molecule. So this neutral ligand, when it is bound to the metal ion center such that cobalt, we get cobalt of three types, that means tris ethylene diamine cobalt, and if the cobalt center is in trivalent state we get 3 positive charge on it. So this is the thing where we have, this is the ethylene diamine backbone, NH2, CH2, CH2 and NH2. This is the first chelate ring, this is the second chelate ring, and this is the third chelate ring. So when first chelate ring is showing, so this is the ball and stick diagram. Usually when we do the X-ray structure we get this type of ellipsoids, that means the atoms we are getting as the corresponding sphere, showing the corresponding electron density related to that particular atom. But in the diagrammatic form we see that this is the corresponding nitrogen. So this nitrogen is starting from here, so this is the first chelate, so this is the first chelate, this is the second one from this nitrogen to this nitrogen, and this is the third one from this nitrogen to this nitrogen. So when we see the three-dimensional view, we see this particular chelate. So this is the front nitrogen and this is the back nitrogen. So that's why this particular curly ring is bold in this particular side and is thinner on the other side. Similarly, this nitrogen is in this particular plane of the paper, but this nitrogen is back of the plane of the paper. So the bold is this side but is thin in the other side. Similarly, we see another situation for cobalt where the ligand is not the ethylene diamine but is EDTA. So for this ball and stick diagram, what you see, this is the only backbone related to this one, which is the ethylene diamine backbone, and this ethylene diamine backbone is present over there, and from this ethylene diamine backbone we have 4 carboxylic acid groups, 2 from the right hand side and 2 from the left hand side. So this nitrogen is functionalized through one oxygen and through another oxygen. So this is one half. Similarly, this nitrogen is functionalized through this oxygen and through this oxygen. So this is another one, which is ethylene diamine tetraacetic acid, that means the EDTA. So when we write the cobalt EDTA complex, the diagrammatically the diagram of this particular ligand would be like this. So all these informations and all these structures we can have from the McMurray and Fay's book. So what we see that most of these geometries, the 6 coordination is most common arrangement for electronic configuration ranging from D0 to D9. If the center is devoid of any d electron, that means molybdenum in +6 oxidation state, which is D0 system but in the 4D level. So it's a 4D0 system, but it also prefers a coordination number of 6 in octahedral geometry. Similarly, a D9 system which is cobalt 2. So if we have copper 2, so this particular copper 2 we can get for the corresponding 3D9 situation, and that also gives rise to a typical octahedral geometry. So further examples, we can have the complexes by metal ion in trivalent series, which are in the 3D series, they are all usually octahedral. So if we have iron in the trivalent state, cobalt in the trivalent state, all will prefer to have a coordination number of 6 in octahedral geometry. Some more examples are there apart from iron or cobalt, and these are belonging to the situation where we have, these are falling within the range of D0 to D9, but they are D3, D6, D5 and again D6. So for a D3 molecule we have the scandium hexaaco molecule. 6 water molecules are surrounding the scandium center in octahedral geometry. Similarly, these two are cyanometalates, where we have the molybdenum, which is a 3D6 system. Similarly, this is the molybdenum, this is iron, which is also hexacyano, which is a D5 situation, and rhodium also, which is a D6 situation, and where we have the 3 charge on the complex, and we get all as the corresponding octahedral geometry. So if we just consider the typical octahedral geometry from the corresponding polyhedron, that means how the polyhedron will look like, the way we have drawn the corresponding geometry is that in this particular case what we have seen, that if we have A4B2 molecule which are in cis geometry, and the polyhedron we can draw is this particular polyhedron. So there are basically these A, B, these are all trigonal faces, trigonal faces of 4 in number. So this is one trigonal face, this is the second one, this is the third one, and this is the fourth one. So 4 trigonal faces above this A2B2 square plane and 4 below. So we have 8 trigonal faces. So these 8 trigonal faces give rise to the name which is octa. So that's why we have octahedral, that means 8 faces we can have. So this is the typical structure of this octahedral complex. So this is one particular trigonal plane, this is the second trigonal plane, this is the third one, and the fourth one is not visible, which is above this square plane. So this is the metal center and 6 donor atoms are showing. So this is a corresponding polyhedral arrangement. What we can see from this particular situation, and this one particular trigonal plane is visible nicely from here. So diagonally opposite side, on the back of this figure, back of this polyhedron, we have another trigonal face, but which are completely in reverse direction. That means this trigonal face point joining this point and this point, which is another trigonal face which is on the back side of this figure. So if we have a corresponding distortion, so how we can get a corresponding distortion in the octahedral geometry? Because whenever we have these different types of donor atoms, like that of our cobalt compound, what we have seen that cobalt with 4 ammonia groups which are and 2 chlorine groups. So, in this particular situation they are not homoleptic, they are heteroleptic complex because we have 2 types of ligands groups present. So, it is the A4B2 type situation, and obviously we will have 6 cobalt ligand bonds are present. 4 are cobalt nitrogen and 2 are cobalt chlorine bond. So, if they are, these 2 bonds definitely will be not equal to each other, but we see that if the cobalt chlorine bond is longer than the cobalt nitrogen bonds, what we see that this particular one, that means we have these cobalt chlorine bonds are longer compared to the 4 cobalt nitrogen bonds which are in plane. As a result, what we see that we cannot consider is as a regular octahedron, because by definition the regular octahedron is a such polyhedral arrangement where all the metal ligand distances are same. So, it has some elongation. So, we consider this as elongation along this direction. So, if the elongation is along the z axis, we consider that the elongation has taken place along this z axis, and therefore, it is an elongated structure of a corresponding typical octahedron. So, we have 2 types of tetragonal distortions. One is the tetragonal distortion like that what we have just seen, and the symmetry level which can change from OH symmetry, because the symmetry was OH, it can be changed to D4H symmetry when 2 ligands along one axis differ from the other 4. That was, we are discussing that the 2 cobalt chlorine bond lengths are different, which are longer compared to the cobalt nitrogen bonds which are 4 in number in one particular plane. In case of copper also, in +1 oxidation state, which is a D9 situation, the tetragonal distortions may occur when all ligands are identical also. That means the Jahn-Teller distortion is operating over there. So, this is the situation, the first situation what we have seen just now. That means we have the elongation either through different types of ligand coordination, like this cobalt bound to 2 different types of ligand groups. One is NH3 and another is Cl, or we can have the copper which is a 3D9 situation, which is not 1 plus, is 2 plus. So, copper in 2 plus, which is 3D9, and when all the ligands are same, that means if all of them are water molecules, we expect that all the cobalt oxygen bonds, copper oxygen bonds are same. But in actual practice it is not happening. We get unequal occupancy of the electrons in 2 levels which are in one T2G level and another is the EG level that we will discuss in some of our future classes. And we see that since the electronic configuration is 3D9, we will have two types of copper oxygen bonds, and we will have a corresponding situation where we get either compression or elongation. So, this is the elongation, this is the compression. So, this is for the corresponding tetragonal system, where we find that this tetragonal system is changing along the z axis. So, the z axis is either elongated or it can also be compressed. So, when we get that these two bonds are shorter compared to the other four bonds, we get a situation where we have then instead of tetragonal elongation, we get a situation where we can consider it as a tetragonal compression. So, this is one sort of situation where we are talking about the distortion which is tetragonal in nature. So, next we will discuss about the corresponding trigonal distortions. Thank you very much.